Hello, I'm Dr. Damikabi Aul, and this is the concluding part of a lecture series on linear programming. In the last part, I introduced to you how to build a linear programming model in Excel, and that part leads to this one. So if you haven't watched it yet, you want to click on the description bar below, and you will find a link to that lecture. In this one, I'm going to talk about Excel's sensitivity report. The sensitivity report is one that is created when Solver is run. It tells you how your models and your answers will change when you change the parameters in the model. Parameters are these numbers that are given in the models. I've painted them all blue. So it tells you the effect on the decision variables and the objective function of changing the different parameters. Let us run a model to start. So I'm going to click on Solver, and I've already set Solver up. I'm going to hit Solve, and 3 reports show up. The one we want is the sensitivity report. So I'm going to click on Sensitivity and do OK. And here is the report for example 1. It calls it a very intuitive name, like Sensitivity Report 1. It is called 1 because it's the first one that is run. So at the top of your sensitivity report, I'll just make this a little bit larger so you can see better. At the top of your sensitivity report is the information that concerns the decision variable. And at the bottom, where it says constraints, is the one that concerns the constraints. First thing you see here is information on the cells that contain all of the values. So cell B2 and C2 contain the decision variables. Cells D6, 7, and 8 contain the constraints, the right-hand value for the constraints. So, I'm sorry, the cell for the used value of the constraints, how much of it is used, is contained in cells D6, 7, and 8. So, let's start with the variable cells. Cell number, cell address, cell name. Name is constructed from the labels that you have used on your model. So if I go back to example 1, I've called it decision variables, and this is type 1 and type 2, and it's used decision variable type 1 to construct a name for the cell. If you don't have any labels, it's optional. It will just leave that empty. In column D here, you have the final values for the decision variables at the top. Next to it, we have what is called the reduced cost. To introduce the reduced cost, I have to introduce a concept called basic and non-basic variable. A basic variable is a variable that assumes a non-zero value in your model. It's a decision variable that assumes a non-zero value. So the final value here for your decision variables is 9 and 4. So it is a basic variable. If there was one that had a value of 0, then it would be non-basic. Your basic variables have no reduced cost. I'll explain what reduced cost is in a minute, but I'll come back to it. The objective coefficient here is the coefficient of the decision variable in the profit calculation. I'm going to borrow a pen. To calculate profit, it is the price profit per item multiplied by the number of items, right? So for the first item, we produced 9 of them. For the second one, we have 4 produced or sold. So the objective function or the profit function is 60 times 9 plus 50 times 4. 60 is given. We gave the profit for item type 1 and the profit for item type 2. 9 is the optimal solution given all of the inputs that solver came up with. So the coefficient here just tells you that these are the values used to run the objective function. The allowable increase and allowable decrease is the change in the objective coefficient that is allowed without changing the final value. So here in this instance, we have an allowable increase of 60. So that means an allowable increase of 40, I beg your pardon. That means that the coefficient of type 1 variable can go up by just less than 40, and the final values will remain the same. Let's go back and put this into practice in the model. So if I click in here, I'm going to make this 99. Allowable increase is 40. 40 plus 60 is 100. So I'm going to go 99. And you will see that the final solution will be unchanged. So data, solver, run solver again. OK, unchanged. The final profit changed because the number we're using to calculate profit has increased, but the optimal solution doesn't change. Now, if we go about 40, the optimal solution might change. It most likely will. So let's do 100 first. Let's walk around that boundary. Solver, solve. Can you see? So once we get to 100, the model changed. Now I'm going to run this again, but this time I want a second sensitivity report to work with. So this is the first one, and here is the new sensitivity report. And this sensitivity report is based on a coefficient of 100. Now what this tells us here, see? Actually, the information I'm looking for is not showing up. We have a non-basic variable because now we're manufacturing 11 of type 1, 0 of type 2. Type 1 is a basic variable, 0 is non-basic. Sorry, type 2 is non-basic because it has no values assigned to it. And usually you would have a reduced cost. But in this case, we don't have a reduced cost. So I'm going to hold off on discussing reduced costs for a minute. I'm going to delete this sensitivity report as well. So we'll go back to the last sensitivity report. So 40 is the allowable increase. It tells us that the coefficient of type 1 can change by 40. It has to change by 40 because before there's a change to the optimal solution. So anything less than 40, and you will be asked to produce 9 and 4. As soon as you hit increase of 40, then it will change. That means then that the range of value over which the optimal solution doesn't change for the first variable is allowable increase, just less than 100, all the way to allowable decrease is 10, so 50. That means that variable 1 can have a value of just more than 50 to just less than 100, and your final optimal solution will not change. It will remain unchanged. Same for type 2 variable. The allowable increase and decrease can be interpreted as the change in the objective coefficient that would leave the optimal solution unchanged. Now, the changes here that we're talking about is all else being equal. So when you make changes to variable type 1. Type 2 is left unchanged. And when you make changes to 2, 1 is left unchanged. So all else being equal, you get no difference. You get no change to the optimal solution. So with type 2 variable, the allowable increase is 10. So that means that the profit can go up to 60. And the allowable decrease is 20. 20 minus 50 is 30. So it means that the coefficient of this variable here, or the profit on type 2, can span the range of 30 to 60, and it would leave the final solution unchanged. I'm sorry. Not consistent. Less than 100, but greater than 30. Greater than 50. So that is how we interpret this. I'm going to hold off on reduced cost, and we will come back to it soon. Let's go talk about the constraint cell. Down here we have the constraints information. Again, we have cell address for the used, where our constraints are, D6, D7, D8. Go back to the model. These are the Ds. It tells us that for the constraints, the name is assembly time, used, inspection used, storage used. Again, it's taken the name from the labels that we constructed here and at the top, okay? And it tells us what the final values are. So when you run solver using the values in the box here, the final value for the constraint that is used, assembly time is 72, inspection time is 22, storage is 39. Now, the constraints right-hand side, these here, again, I'm going to omit shadow price and come back to it. These values here on this side, those are the maximum allowable resource, maximum available resource. We can use 100 of assembly time, but no more, 22 of inspection hours and no more, and 39 of storage and no more. We used 39 of storage when we had 9 of the type 1 and 4 of type 2. We used 39. That means we used it all up. Inspection hours, we used them all up. Assembly time, we didn't. So when resources are 100% used up, the constraint is said to be binding. It's said to be binding. You can't use any more. You can't improve the system anymore because you've used up all of the resources available. So inspection time and storage, they are both binding constraints. However, assembly time is non-binding. What we mean by non-binding is that there is slack in the system. We haven't used all of the resources available. We have extra left. So that is definition of slack. When the number used is less than the number available, then you have slack. When number used is equal to number available, then it's a binding constraint. So looking at the report on constraint, we can tell that the first one is non-binding, but the other two are binding. Now is the time to talk about shadow price. The shadow price is the improvement in the objective function when you increase the available resource. If you increase the available resource, the objective answer will go up by 10 for inspection used. And if you reduce it by 1, it will go down by 1. So shadow price is the change in the formula that you're maximizing. It's the change to total profit when you add a unit of resource or take away a unit of resource. Shadow prices are only available for resources that are binding. If there is slack to the system, then there is no benefit to increasing the resource by 1 unit. Look at assembly time. We've used 76 out of 100 hours. There is no benefit to increasing assembly time to 101 or 102. There's a lot of slack. Whereas with inspection time, if you increase inspection time by 1, then the profits will go up. So the question you ask yourself is, if the profit that can be derived by increasing inspection time by 1 is 10, should we increase inspection time? And the answer is absolutely, if the cost of an additional inspection hour is less than 10. So the shadow price helps you weigh the cost and benefits of doing business. The shadow price for storage is 13.33. So if you increase storage by 1 unit, everything else staying the same, the objective function will go up by 13.33. So we will demonstrate. Let's go demonstrate that actually. So go back to the model. I'm going to return this value here back to 60. And I'm going to rerun solver just to get back to the point we were when we started this. So run solver. Okay. As you can see, profit is 740. If I release the slack on inspection time, make 1 more hour of inspection time available, and rerun solver, you will see that the profit here will go from 740 to 750. So solver, solve. Okay, can you see? Now, the optimal solution changed. This is not what the constraint section is about. For the constraint section, it tells you the change to the objective function. That's it. So the shadow price for inspection time is 10. We had 22 hours when we built the model. I'm going to go down by 1 to 21 hours. And again, the objective will reduce to 730. So solver, solve this again. Okay, can you see? Now it's 730. So that is the concept of shadow price. Now, the allowable increase is infinity because 1e plus 30 is like 10 raised to power 30. That's a really big number. This allowable increase is the increase that is allowed for these resources over here and for which the shadow price will be valid. The allowable decrease is the total number of decreases allowed for which the shadow price will be valid. So let's go back. Our right-hand variable was 22 when this report was built. So 22. Allowable increase, go back. Allowable increase is 4. Allowable decrease is 4. So let's go to 26. We are adding 4 units. Shadow price is 10 per unit. So we should go from 740 to 780. Solver. Solve. Okay. We went to 780. Sometimes it's not quite on 20. It's not quite 4. It might be 4 point something. So let's go to 27. 27 had 5 units. So solver and solve and okay. Can you see? No more benefits. No more benefits. That's where we are. Same with this. It can go up or down by the allowable increase and decrease, and then there is no more, the shadow price is not valid anymore. Okay, so that is us with the report. I'm going to run another one and then go over the same thing again. So let's go to the second model. It's correctly built, so all I'm going to do here is hit solve. Make sure that my objective is in the right place, is maximizing. My decision variables have to change. Okay, so delete. Here are my decision variables. I'm going to delete the constraints. I think I might have to try this again. I'm not sure if it's in the right spot. So let's delete the constraints, add constraints. These values over here must be less than or equal to these values over here. Okay. My non-negativity constraint is in and it's simplex. Hit solve, hit sensitivity. Okay. So we have two of the decision values that are 0. In this system, it says manufacture, hit OK, manufacture 0 of X1, 0 of X2, and 18.33 of X3, and that gives you the maximum profit. You can't do better. For constraint 2, it's binding. For constraint 3, it's non-binding. We've used 0 of 10. So there's a slack of 10. Slack is available minus used. Here, there's a slack of 100 and something. So let's go look at the second sensitivity report for this one. Sensitivity report is split at the top for the variable, at the bottom for the constraints. First is cell name, cell address, then cell name for the decision variables. The final value is 0 for the first one, 0 for the second one, and 18.33 for the first one, for the second one. The reduced cost for the 0 values are given -4 and -2. And for the one that is non-zero, there is no reduced cost. So, concept of basic and non-basic. These two that have 0 values for the decision are non-basic, and a basic input is the one with a number. Non-basic inputs typically, basic inputs have no reduced cost, because reduced cost is the cost of turning a non-zero input zero. Sorry, a 0 input non-zero. In order to be able to produce item X1, we have to improve on the coefficient of X1 by 4.33. So it is the cost. I know that it can be confusing because it's a negative amount, but basically look at the cost in the same light as the allowable increase. The cost is the cost to make that non-zero decision value, make the 0 decision value non-zero. Now, reduced cost, as confusing as it is a redundant information, because for a 0 variable, the reduced cost is the allowable increase. In order for this value to no longer be 0, you've got to increase the coefficient by 2.66. So let's go back and put this into practice. For the 2.666, so we just say 2.7. Okay, I'm going to add 2.7 to 4, so that gives me 6.7. Let me add a few zeros so that it's clear what we're doing. Now I'm going to run solver. So data solver, this was the last model I ran, so when I run it again it should work. Okay, so now see what happens. These two have become 0. This is non-zero. So the reduced cost is the improvement that is necessary to the coefficient or profit in this case in order for the decision value to become non-zero. Okay. Allowable increase, say, is the amount by which you can increase your objective coefficient and still keep the final value the same, still keep the decision values variables the same. Okay, so for this one, you increase it by 4 instead of 4.33, you still be good. If we increase this by 2.6, there should be no change to the objective function. So instead of 2.7, we'll go 6.7, we'll just do 6.6. Run solver, hit OK, and OK. So again, as a reminder, the allowable increase is the increase in the objective coefficient before the final values change. If you increase it just below the allowable increase, then the optimal solution is still the optimal solution. It's unchanged. But if you go up to the allowable increase, then the optimal solution will change. And the decrease is the amount of you allow the model to reduce by. So basically this one, you can take the objective coefficient down by infinity. It can go to 0, negative, whatever, and still the final solution will be unchanged. Same with this little value here. Whereas for variable 2, you're only allowed to decrease it just shy of 3.2 before the optimal solution changes. Again, let's go look at the constraints. The cells, cell address, cell name, the final value in the cell, the fact that 110, the second one, is a binding constraint, whereas the other two constraints are non-binding. There is a slack in here of 176, and there is slack in here of 10. Now, there is no shadow price when you have slack. Shadow price show up only when you have a binding constraint. And it is the amount by which the objective function will change when you change the constraints here. When you increase or decrease the available resource by 1 unit, then the objective function will change by 1.33 for the second one. Let's look at the third model and try this one more time. So, hit solver. My objective function is right here in F2. My decision variables are here. I'm going to delete and then add my constraints. Okay. I'm going to solve and ask for the sensitivity report. Okay. This is the sensitivity report for the third one. Before I go to the sensitivity report, the first constraint is binding, the second constraint is binding, the third one is non-binding. The decision variables are basic variables, and these here are the coefficients of the decision variables. Going back to the sensitivity report, same information. We have the final value. We have the coefficient. There is no reduced cost because both of the variables here are basic variables. Reduced cost typically only apply to variables that are 0 because it is the amount of increase to your objective in order for the 0 value to become non-zero. Hope that makes sense. Allowable increase for the first coefficient is 300, decrease is 600. Sorry, for the first coefficient is 1000, decrease is 600. That means the first coefficient can go from 4000 to 240. Also, the constraint side of things, we've used that much labor. I'm going to open it up so you can see. We used up all the labor, that is binding for constraint. We used up all the stone, that's binding. We did not use up all the lumber. So we have a shadow price for labor and a shadow price for stone. Shadow price for labor is really, really small. That is the change when you increase labor by 1 unit, which is not surprising because labor is huge, right? 1 unit compared to 400,000 is very, very small. Your allowable increase, for which this shadow price is valid, is up 100,000, down 100,000. So our stone allowable increase is 50, decrease is 30. And for lumber, there is no binding constraint. So you can increase it to infinity and reduce it by 75,000 before you start to suffer a loss. Okay. And 75,000, the allowable decrease, by the way, is the difference between the constraint and used. This is available and used. Basically, you can take away all of the slack in the system and there will be no change to the system. Okay, so there it is. Have a good day. That is the end of the linear programming section.